Hi grade 11s, my name is John. Good to be with you for this Learn Extra program. And we're going to be looking at a fascinating topic today. It's called chemical bonding. So when we break up chemical bonding, the first thing that we're going to be looking at is different types of bonds. Now, I wonder if you can remember some different types of bonds that you might have come across in previous grades. Well, hopefully you will remember about things called ionic bonds, covalent bonds, and maybe even metallic bonds. We'll have a closer look at them shortly. And then we'll take a detailed look at this idea of covalent bonding. So let's just underline that. It's probably the most important type of bonding that we're going to do. And we're going to be looking in detail at covalent bonding. And associated with that is this idea of electronegativity. Electronegativity is a model that we use to determine what type of bonding is happening. It tells us how electrons are going to be held in their bonds. So we'll get to that shortly. Shapes of molecules is another important idea, and you should know that not all molecules have the same shape, and that can determine whether a bond or a molecule is actually polar covalent or non-polar covalent. Once we've looked at that, we've got quite a lot to do. We're going to look at bond energy and bond length. And the final thing that we'll look at is oxidation numbers, because oxidation numbers tell us something about where the electrons are in a bond and how the atoms are linked to each other. So let's get started straight away, and let's start off by asking the question about the types of bond. Now, I mentioned earlier that there might be some words that you've remembered, and those words might have started with the word ionic. Ionic bonding. And ionic bonding, let's remember what happens there. We've got a metal reacts with a non-metal. And we think that what happens in this model is that the metal loses electrons and the non-metal gains those electrons, gains the electrons. And so the metal becomes an ion, which is positively charged, and the non-metal becomes a negative ion, and we give them special names. These are known as anions, and these are known as cations. Okay? Now, what's important here with our ionic bonding is the examples that you get them. You get them in some things that are called salts, like your ordinary table salt, sodium chloride. But it's not a single entity. So it's not one sodium atom and one chlorine atom. It forms a crystal lattice in which you have many, many thousands of these positive and negative ions. We sometimes draw a little unit cell, a little square, to represent how these ions are collected. So I'm just going to color these in so that you've got them. Let's pretend that the green one stands for the positive ion. Now, its nearest partners will all be negative. So I'm going to make the nearest partners being pink, so that one there. And down at the bottom, which you can't see, behind in the background there, let's just draw it in white. We're going to have another one that's seated at the back there. That one will be pink as well. So I'm just going to put the pink in, and we'll make it right down there at the base. So this one has three partners, three closest neighbors. Remember, we said the green is going to be positive, and that means the pink is those are all negative. But if we fill those in and carry on the pattern and put in some more greens, then we'll recognize that one must be a green. which means that this one down here at the bottom must be a pink. But then notice that this one must be a green and that one must be a green. Now, if you do that, you'll see that each of them has 3 partners. The total number of positive ions is 4, and the total number of negative ions is 4. So the ratio is 1 to 1. And that's why for something like sodium chloride, we'd write it as NaCl. It's not saying that there's a molecule of 1 sodium atom and 1 chloride ion, but there is a collection, many, many thousands of atoms, and they're held by these electrostatic forces in arrangements like this. This is called a cubic arrangement. There are other arrangements that might happen, but it's a ratio that happens within ionic bonding. Okay, let's move on to the next type of bonding, which is covalent bonding. So let's write the heading here. And the important thing here for covalent bonding is that what we get is usually takes place between either hydrogen and a non-metal, or another non-metal, any non-metal, and another non-metal, different non-metal. In both of these cases, we find that we get sharing of electrons. Now, these electrons that are involved in bonding are those in the outer energy level. Can you remember the name that we give for those electrons in the outer energy level? Well, hopefully you can. It's got an interesting name, and we're going to use it quite often. We're going to say that that name for the outer energy level is the valence electrons. So sharing of the valence electrons. Valence electrons. I just want to make a point that these are in the outer shell, the last shell, the outer energy level. And in fact, these ones that are lost and gained with ionic these are also valence electrons. Valence electrons. So make sure you've got that idea. Sharing of valence electrons and losing and gaining of valence electrons. Now, the next idea, we'll come back to covalent bonding shortly, but the next type of bonding that I want to discuss is metallic bonding. Metallic bonding is a very special type of bonding. It happens, as it suggests, between metal atoms. So this is metal atom plus metal atom, and it's the same metal atom. These are the same atoms. So it's typical of what might happen in something like iron or something like magnesium. We're going to find that we get an arrangement of atoms. So I'm just going to draw them like that. They are collected like that. Now, the metal atoms, what you need to understand about metal atoms is that they don't hold on to their valence electrons very tightly. The metal atoms actually let go of their valence electrons quite easily. They have what we recognize as a low first ionization energy. They allow electrons to go, particularly those in group 1, group 2, and group 3. Their ionization energies generally are quite low, the first couple of ionization energies, the outer shell ionization energies. So they can let go of electrons. So when they get together, what happens is you've got these electrons are allowed to drift. So we sometimes say that these things that I'm drawing as negative, think about them as being the electrons, and they're allowed to move. It's not that this one was belonging to this atom, or that one was belonging to that atom. They can move freely. So they are known as delocalized electrons. Delocalized electrons. And sometimes the terminology is used that these are kind of like little positive kernels. These are little positive nuclei with the inner electrons, and then there are a whole lot of negatives that are around them. I'm saying that's positive. It's not just +1, but it's positive generally. And we've got these electrons that are free to move. Now, the electrostatic forces between these different nuclei or kernels, not nuclei, but the kernels, the atoms that are positively charged, they're not in one particular direction, and they're quite flexible. And that's why metals, you can bend metals, you can stretch metals, you can roll metals flat, but they are still very strong. And they generally have quite high melting points. So there are strong forces, but it's this model of bonding that helps us explain other properties of metals, such as the fact that metals generally conduct electricity, and they are good conductors of heat because the electrons vibrate and they can move through the bond as a sea of electrons, and that gets everything moving a little bit faster, and that's why they can conduct electricity and conduct heat. So that's a model for metallic bonding. I hope you've got that. Doesn't come up very much, but I thought we needed to mention it. It's important to recognize in all these three cases, the important word is this word of valence electrons. Now, you might say, but you know what? There's another word that's similar, and I can't remember it. It's also valence something. Valency. That's right. Now, let's just go and have a look and see how these are related to each other. The easiest way to do that is to look at the periodic table. So let's go and have a look at the periodic table of the elements, and here we have one. This one was taken from a past exam paper, so it's not very colorful, but we can show some things. First of all, what I want you to notice is that we've got the metals on the left-hand side of this periodic table. So over here, all the way up until group 3. So that's group 3, and there's group 4, group 3 or 13. So these are the metals. We've got some semi-metals as well over here, but let's just take. There's the start of the semi-metals. So everything on the left-hand side of this is a metal. So these are the metals. I want to make sure that you've got that. And the metals generally lose electrons to form, they generally lose electrons, or they've got electrons available to give away. These are your non-metals. They want to gain electrons. So there's your non-metals. And what we need to notice is this group, group 8 or group 18, those are known as your noble gases. Noble gases. The reason that they're called noble is because they don't bond. They're inert. They stay as they are. Now, this gives us the whole key to understanding bonding. They have a filled outer energy level. They have a filled valence shell. And so the people that were looking at the noble gases decided, that's an interesting idea. We've got a filled outer shell. So let's play a game. Let's see. Everything else wants to become like a noble gas. So if we take a look at that, we see that there are important numbers. And at first, the chemists started to say, well, look, it looks like everything wants to have 8 electrons in its outer shell. It doesn't always happen. It happens for the second period and the third period of the periodic table as we have it today. But what we need to recognize is it wants to be filled. And for those two periods, we can say 8 is the magic number. But I like to think about it as the magic number is trying to get the same number as the noble gases. So if I just erase my writing there over the word noble gases for a minute, you'll see that everything wants to get to either number 2, number 10, number 18, or number 36. If it can get to those magic numbers, same number of electrons in total as the noble gases, then we'll say it will be stable. So how does it do it? Well, let's take an example and we can see how it goes. So if we take a look at a metal, for example, let's focus in on one of my favorite elements, magnesium. So number 12 on the periodic table, magnesium. Now, notice it has an atomic number of 12. That means it has 12 protons and 12 electrons. And if we look at its position, it's in group 2. So the inner electrons are the ones are the first 10. The outer electrons, or the valence electrons, and that's what I wanted to show you here, is the valence electrons are easy to determine. It's the same as the group number. So from the left-hand side here, that's 1 electron, that's 2 electrons. So magnesium has 2 electrons. Now, when we're dealing with valence electrons, what we need to recognize is one way to show the valence electrons is to draw the Lewis diagram. When we draw a Lewis diagram, the first thing we do is we write down the symbol. And then we look at it and we say, okay, it's number 12. What's the closest noble gas? Well, 12 is closest, the one before it was number 10. So we say 12 minus 10 is 2. That gives us the number of valence electrons. So when we draw the valence electrons, we've got a choice. We can draw them in the Lewis structure either as a cross, 2 crosses like that, or as 2 dots. So another way of drawing that same structure, Lewis structure for magnesium, you could quite easily have drawn it like this. Magnesium, 2 valence electrons with 2 dots like that. So what's magnesium going to do? Magnesium, when it bonds, wants to get to be like a noble gas. So I hope you can see that what's most likely to happen to magnesium is magnesium will start off with these 2 electrons, and it's going to get to lose those electrons. It's going to give them away. And magnesium will then end up being Mg2+, and there will be 2 electrons somewhere that have been given away. Notice I haven't drawn the crosses in there, but this whole thing has now got a charge of 2+. It needs to give them to something else. What will it give them to? Well, when we've got a metal bonding with a non-metal, then the non-metal is able to take those electrons. So very important, let's choose an example where this can happen. And we're going to choose oxygen as an example. So oxygen, let's have a look at it. The word we want to write, the element is oxygen, the symbol is O. Look where it is on the periodic table. It's in group 16 or group 6. It's number 8. It needs to gain 2 to become 10. So from 8, it would gain 1 to become 9. To become 10, it would be like neon. So that's what it wants to do. So what we need to recognize, how many valence electrons? Well, it was in group 6. So I'm going to draw 6 electrons around the oxygen. First 2 like that, then the next 2 like that, and I'm going to pair them up like that. So these ones are now paired electrons. These are unpaired, and they've got space to either gain electrons or they could possibly even share. So what happens if magnesium comes along in the presence of oxygen and we were to burn some magnesium in oxygen? What's going to happen is the magnesium's 2 electrons are going to be gained by the oxygen, and this is exactly what would happen. We would get oxygen going to form this structure. Those 2 electrons that we had with magnesium could be gained, and instead of sitting there where I had them, they are now going to move. So let's move them. We're going to move them there and there. So we'd end up with those electrons being gained. But now you can't just gain an electron. You've got to change the charge. It now has 2 electrons more than protons. So it has the original number. Look at the periodic table. Again, oxygen is number 8, so it had 8 protons, 8 electrons. If it gains 2 electrons, it's got 2 more electrons than protons. What will its charge be? Well, if I have 8 positives, 8 protons, and 10 electrons, I hope you can see that there are more negatives than positives, and so the overall charge here is going to be -2. That's going to give you a charge of -2. 2 more electrons. And so if we did this, and reacted magnesium and oxygen, we would form a new substance held together by strong electrostatic forces, and that's going to give you magnesium oxide, a lovely white powder, after it's burnt with a bright white flame. So if you've got sparklers that you've seen at a celebration, fireworks celebration, you will notice that's mainly magnesium, lovely bright white flame, and afterwards you've got this white powder that just crumbles in your hands. That's magnesium oxide, and what we would say is that bonding, notice, is between a metal and a non-metal. So magnesium oxide is an example of an ionic substance. It has an ionic bond because it's held together by the attraction between the positive magnesium and the negative oxide. This is oxide. Please notice the oxygen changes its name because it's now bonded to magnesium. We write it as magnesium oxide. Now, one of the things that you might be struggling with is how do we write these formula? And there's a little trick, and that was the word that I wanted to get to you. We were talking about those electrons in the outer shell. We said they were valence electrons, but there's another word. The number of electrons that a substance has to lose or gain or share to become stable. So we recognized magnesium is going to lose 2 electrons, but notice oxygen gained 2. So the difference, it has 6 valence electrons. Please notice this. It is in group 6. Oxygen has 6 valence electrons, but it only wanted to gain 2 electrons. The number it has to gain is called its valency. Valency. And so just as a quick rule, what I'm going to say to you, you need to learn the valency because it will help you to write the formula correctly. Here's the way I do it. I say to myself, if it's in group 1, it has a valency of 1. If it's in group 2, it has a valency of 2. In group 3, it has a valency of 3. In group 4, valency of 4. But now from these, the non-metals tend to gain. So the valency in group 5 or group 15 is going to be 3. Valency in group 6 is 2. Valency in group 7, the halogens, is 1. They all need to gain 1 to become stable like the noble gases. So I think we've got the idea there in terms of the difference between valency and valence electrons. Very important that you understand that and you understand how it works to make formulae. Please learn that and make sure that you've got it sorted out. Now, you might be saying, but hold on, there aren't only ionic compounds. What about when nonmetals react together? What happens when nonmetal reacts with hydrogen? That's when we get covalent bonding. And I want to use the Lewis diagram to illustrate covalent bonding. So covalent bonding, the first example I'm going to do is I'm going to do the example of hydrogen plus chlorine. And I know that if we were to draw the substances, we would write H2 and Cl2. I'm just going to worry about the atoms. How does a hydrogen atom join together with a chlorine atom? So there's my H, there's my Cl. Now I'm going to draw the Lewis structure. Very important that you learn to draw the Lewis structures. So we write down the symbol, then write down and indicate the valence electrons. Well, with hydrogen, it's not too difficult because look at the periodic table. Hydrogen's the first one. It only has 1 electron. It's number 1. So we're going to write H, and let's put a little dot over here. I'm going to use a different color pen to separate it, and I'll put the dot over there. What about chlorine? Well, chlorine is number 17. Over here, check it out. Let me just erase so that you can see. And I'm going to try and enlarge that so you can just get a closer look. There we go. Chlorine, number 17. I hope you've got that very clear. It's 1 below the noble gases, but number 17, it's in group 7. sure that you can see that it needs to get 1 to become 18, but because it's in group 7, how many valence electrons has it got? Well, 7 valence electrons. So we're going to just close that down, and we need to fill in around the chlorine 7 little crosses. And I'm going to put them in like that, 2 there, 2 there, 2 there, and 1 over here. So there's my chlorine atom, hydrogen atom. What's going to happen? As these come together, remember, hydrogen wants to become like helium, the noble gas. Chlorine wants to become like argon. And we need to make sure that we've got that right, like the noble gas. So what's going to happen? Sometimes we're going to get some sharing taking place. So let's just highlight those. Hydrogen bumps into chlorine, and they join together and they form this molecule, which is a new molecule. And what I want you to see is that now, how many electrons has hydrogen got a partnership with? Well, I hope you can see there's 1, 2. So hydrogen is just like helium. It's got its 2 electrons. And what about chlorine? Well, count up the chlorine. 1, 2, 3, 4, 5, 6, 7, 8. So it's got its octet number, the number 8, sometimes called the octet rule. But the valence shell is now full. So this pair of electrons is shared. It's a shared pair. It's shared between the hydrogen and that's what covalent bonding is all about. It's about sharing electrons to get the outer energy level full. Sharing electrons. We say that we've got a shared pair of electrons, and this is known as your bonding pair. Right, there's your covalent structure. We're going to come and talk a little bit more about the hydrogen chloride molecule. What results is one molecule. Very important for you to know that this isn't a crystal. It's one entity, a molecule. It has a certain shape. It has a certain structure to it. And we need to understand those principles very clearly. So there's sharing of electrons. In this case, the hydrogen is much smaller than the chloride or the chlorine atom. So hydrogen is a smaller atom, so there's a little bit of unequal sharing. And because there's unequal sharing, what we're going to suggest is that something interesting happens, that this pair of electrons is pulled more to the chlorine side. So this pair of electrons is going to be pulled more to that side, and the end result of that is, unfortunately, hydrogen misses out a little bit. It becomes slightly positive, and the chlorine end, chloride end in this case, hydrogen chloride, becomes slightly negative. We say we've got two ends, one positive end, one negative end. Now, when you think about that, there's a special name for it. It's got two opposite ends. Two opposite ends is known as a pole. So we have north and south. They're opposite in nature. We have a magnetic north pole and a south pole. So we say it's a dipole, two poles. This is also an electrical dipole. Positive end, negative end, and we'd say, therefore, that this bonding is known as polar covalent, and the molecule is a dipole. It's polar molecule. One end is positive, one end is negative. This isn't the only type of covalent bonding you can get. You can also get covalent bonding where there's equal sharing. I want to just do one example of that. It's a very quick example, and then we'll move on. The example I want to use is the hydrogen atom, or the hydrogen molecule at least. Each of the atoms has one electron, so this one has one, this one has one, and when we bring them together, then what's going to happen is this moves together like that. They share a pair of electrons. There's your bonding pair. Each of them has 2 electrons around there. This is equal sharing. We get equal sharing. And because we've got equal sharing, we recognize that there isn't a positive end, there isn't a negative end. This is known as non-polar. It's a non-polar molecule and it's non-polar bond. A non-polar covalent bond. Non-polar covalent bond. The molecule ends up being non-polar as well. Now, that might seem to be quite confusing. How do we know when something is polar covalent and when something is not polar covalent? Well, there was a very clever man, and he decided to draw up a scale. His name was Linus Pauling, and Linus decided to make the scale. He called it the scale of electronegativity numbers. And I just want to show you, it was right on our list at the beginning. We said that what we're going to do is we're going to talk about types of bonds, which we've done, covalent bonding, and electronegativity. So that's the next idea that we're going to talk about right now. Pauling's scale of electronegativity numbers gives us an indication of, in a covalent bond, who's stronger, how are the electrons being shared. Are they being shared equally or are they being shared unequally? Well, the rule is quite easy. Diatomic elements, when you've got 2 atoms of the same sort, then they're going to share equally. But when there's a difference of electronegativity, then the one end is going to get more electrons, and the one that is less electronegative is going to get less of that share. So what we've done is, on the periodic table, we've actually recorded those numbers. So I want to show that to you and give it to you as an example, just very quickly, the idea of electronegativity. So if you take a look at the key on your examination data sheet, that periodic table, you will see there's this word electronegativity over there. There we go. And the number over here is the electronegativity number of the particular element. So if you take a look, the one that has the highest electronegativity is fluorine. It has an electronegativity of 4, but if you take a look at a metal like potassium, it has an electronegativity of 0.8. Low electronegativity says it's not really interested in electrons. It will give its electrons away. Whereas fluorine wants to gain its electrons, wants to pull them closer to it. It's likely to become more polar. So we sometimes look at the electronegativity difference, number difference, to determine, is the bond polar covalent or is it nonpolar? If the difference is 0, then it's nonpolar. If it's slightly more than 0, we kind of say, well, it's almost nonpolar. But if it's bigger than, say, 0.5 or 0.4, then we say, no, this is a polar covalent bond. And if it gets much bigger, like 1.7 or 1.8 or even 2, then it's more likely to be ionic, or it has a percentage idea of being more ionic. So electronegativity numbers are very important, and they give us an idea of whether something is polar covalent or non-polar covalent or even ionic. Okay, I want to just move on then to the next idea, which is a very important one, and that deals with the shapes of molecules. Now, remember I said to you that hydrogen chloride can be represented as 2 atoms joined together. Now, I want to show you. If we've got 2 atoms, let's take this little piece of press stick and this little stick here representing a chemical bond. And what we're going to do is we're going to say that hydrogen is the small atom, chlorine is the big one, and there's the bond. Now, can you see that they're in line with each other? When we've got 2 atoms, there's only one formation that you can get. You can get them closer together or further apart, that's true, but they'll always be in a straight line. Therefore, we say a molecule like this is a linear molecule. Notice it's in a straight line. The angle between the atom is actually 180 degrees. You can draw a line between the nuclei and that bond angle. Sometimes we talk about bond angles. We say it's 180 degrees. It's in a straight line. Okay, so that's a very important example. The example that I've given you, it could be chlorine and chlorine or hydrogen and hydrogen. This one I've represented a big atom here, small atom here, representing something like hydrogen chloride. The big one pulls the electrons to its side, so it's going to become more negative. This one becomes a little less negative, so this is positively charged, this one is negatively charged. So it's a polar molecule. The bond is polar covalent, and the whole molecule has two ends. So the molecule is polar covalent as well. Okay, oh, sorry, it's polar. We don't say polar covalent molecule, but we say the molecule is polar. Okay, so what happens if we have more than two atoms joined together? Well, I'm going to start with the idea of, let's say we have one atom and 4 bonds, because that's a very common example. It's a common example because it involves carbon. So there's my one bond, there's my second bond, there's my third bond, and let me get another one of the same length, or approximately the same length. I'm going to change that one because I don't think it's exactly the same length. See that that one is more or less the same length. And you might think that's the best way to orientate 4 bonds. So we could attach a hydrogen to this one, hydrogen to that one, hydrogen to that one. But as it turns out, this isn't the best way to join 5 atoms together. They're not a bond angle of 90 degrees. There's a better way of doing it. If we flatten those 3 and we raise this one and put it in over there, then what we'll get is this structure. And I'm just going to try and stand it up on the desk, hope that it doesn't fall too much. That structure, as it's standing over there, is a really nice tripod-ish structure, and I can turn it around and it looks almost the same. See, if I turn it around, now mine's not, I've just built it here, but it looks almost the same from whichever side you look at it. This is known as a tetrahedral because it's got 4 bonds to it, 4 bonds, 4 sticks, and they're spread apart as far as possible from each other. That's an angle bigger than 90. It's 109,4 or 109,5 degrees. They're far away from each other. Now, this forms the basis of many non-metal and molecule structure and their shape, and it gives an important property to them. So I want to just keep that there because we're going to talk about it in a minute. So what we're going to say here is tetrahedral involves 4 bonds, and the most common example that we're going to look at with tetrahedral is the example of methane. Now, methane is CH4. Now, I want you to understand something about methane. If you look at carbon and you draw the Lewis structure of this molecule, Lewis structure of the molecule, we would draw something like, beg your pardon, four electrons for the carbon, and then let's change the color and put in a dot for the hydrogen. We would draw the structure like this, even though we know the shape isn't at 90 degrees to each other. We know it's the tetrahedral shape. This bond we'd recognize is a single bond. There's a single bond. They're sharing a pair of electrons. It's one bonding pair of electrons between those 2 atoms. So we've got 4 single covalent bonds. 4 single covalent bonds. Having said that, what we need to recognize if we look at the electronegativity difference between carbon and hydrogen, that these are actually polar covalent. Okay, just show that to you again. Hydrogen is 2,1 and carbon is 2,5. So it's not 0. There is a difference between them. It's not a very big difference, but there is a difference, and we would say that this bond is slightly polar covalent. But the molecule, because it's symmetrical like this, The molecule is not. So even if the carbon was pulling down over here a bit and pulling up over here and pulling up over there, the molecules are equally distributed. So there's not one end that is positive and the other end that is negative. But the molecule overall happens to be a non-polar molecule. So even though we've got a polar covalent bond that is between carbon and hydrogen, we'd say, and this is the important thing I want you to know, the molecule is non-polar. The reason is because of its shape. The shape is symmetrical. Okay, now we've got two other examples that are based on the tetrahedral. And the example I'm going to do is the pyramidal shape and use the example of ammonia, and then water is the next one, which is angular. So they're based on the pyramidal, and we're just going to collapse them down. When we get to ammonia, ammonia is NH3, as I've drawn there. So instead of having four hydrogens, like in methane, it doesn't have four hydrogens. It has something else. It has three hydrogens. Now look at what the shape has changed. This top bond is 2 electrons from the nitrogen. That is 2 electrons from the nitrogen. It's a lone pair, whereas there are bond pairs over here. This is no longer tetrahedral because it's not symmetrical anymore. So this is the negative end, and this is the positive end. So the whole molecule becomes polar. It's no longer a non-polar molecule because here you've got a big collection of electrons. All the electrons are negative, whereas here the hydrogens are going to tend to lose their electrons. The electrons are pulled towards the nitrogen. So this bottom bit here becomes positive. The top bit over here becomes negative. So in the pyramidal structure, and we can represent this in the Lewis diagram as well, we get a lone pair, and then we get the hydrogen bonds, the hydrogen bonding pairs over there. And what I want you to see is these ends are positive, which is the bottom end. So where the hydrogens are, that's positive. The lone pair, it's negative. The delta just means it's a small negative. It's not a whole negative charge, just a small negative. Now, what happens with water? Well, I hope you can see that with water, we have oxygen in the middle, but we don't have 3 bonds, we only have 2. And what happens is that angle closes down, and we get another lone pair sitting over there. So water is a strange example, because the shape starts from a tetrahedral, and it ends up being 2 lone pairs, which kind of repel, and they push down on the hydrogen. And over here, we've now got a very polar molecule, because you've got 2 concentrated regions of negative charge, delta minus, and 2 areas of positive charge. The shape overall is angular, and I hope you can see that from that little stick model. If you're battling with the shapes of molecules, please go and build some for yourself. Get some sticks and some press stick and build them yourself, and that should help. I just want to draw the picture of the water molecule so you can see where that lone pair is. Oxygen starts off with 6 electrons. So there's the 2 pairs. This one, that's the lone pair. This one is now the bond pair, and this one is the bond pair. But this angle is just a little bit bigger than 90 degrees. That end is delta negative, and this end is delta positive. So the molecule overall, the difference between this, the bond between hydrogen and oxygen, is polar covalent, and the molecule is also a polar molecule. It is a dipole, polar molecule. Okay, if I go back to my original structure of this lesson, let's check how far we've got now, because I think we've covered more than I had originally intended to. In terms of that, we've done electronegativity. Shapes we've done. Polar covalent substances. That's what we've just done. We've said the molecule is polar covalent because of the shape. So remember, water is a polar covalent substance. So is ammonia. It's a polar covalent substance, whereas something that's organic tends to be non-polar covalent. Right, the next thing I want to look at very briefly, not going to spend a long time on this, is bond energy and bond length, and then we'll go straight into oxidation numbers. So let's go to that slide over there and make sure that we've got it. Now, what is bond energy? Well, it's very easy to get the idea. What we've got, taking this model, which was our water molecule, imagine that there's hydrogen here and hydrogen there, the energy to pull and break this bond. How much energy is stored in this bond? How much do we have to pull to break the bond? Now, it's easy to pull it in a model like this, but bond energy is really that. When we're doing chemical reactions, we recognize that the bond, there is stored chemical potential energy, stored energy. And what we have to do to measure that energy, we have to either break the bond. We sometimes have to calculate if we break the bond, how much energy do we have to put to break the bond? And then we can also calculate how much energy we need to make a bond, make a new bond. And there are calculations and tables that we will work with. Bond length is related to bond energy. Depends on the size of the atoms, depends how close they are, depends on the temperature of their reactions. If they're moving too quickly, they won't attract, they won't form bonds. But if they are of the right temperature, they move at the right speed, they'll form a bond of a particular length. Every bond has its special length. So we need to recognize that's related to the energy. It's how far the distance between the atoms, how far the atoms are apart. Atoms are apart. And it's related to bond energy. If they're held tightly, they're going to be close together. If they're further apart, easier to break. I hope that makes sense. Now, one of the obvious things that they sometimes ask is a question on calculating bond energy. We're just going to take a look at one example of one table just very quickly, just to show you a particular example. So you might be given a table like this, where it gives you pairs of different atoms. And take a look here. The hydrogen atom, short bond length, high energy, 436 kilojoules per mole. And notice that the radii of the atoms is only 120, so they're actually overlapping very closely together. Take a look at another one where you have a double bond, also more energy. So the more bonds, the more energy, but notice here they're a little bit further apart because the size of the atoms are bigger. The radii are bigger, but that's very close to the atomic radii, so you can have a look at that example. Between hydrogen and oxygen, 464, the bond length is 96, but the molecules, the radii, are bigger. So you can see there that there's a lot of overlap between those two. And so we can use a table of data like this. And here's the example. Use the equation and answer the question below. So we've given this. 2H2 plus O2 gives us 2H2O gas. It's all gases. Determine the energy required to break the bonds. So in this particular example, what we were asked to do is to take a look at the reactants, in this case the hydrogen and the oxygen, and to see how many moles we've got and then calculate the energy. Well, let's have a look. Hydrogen, there are 2 moles, so we recognize we've got hydrogen stuck to another hydrogen, and we've got hydrogen stuck to another hydrogen. From the table of our calculation there, 436 is what is required to break one of those bonds. So 436, 436. I'm going to add those up because I've got 2 of those. Then what about the oxygen? Oxygen to oxygen is over here, 497. I've only got 1 of them, so I'm going to put oxygen, double bonded oxygen, 497. And so to calculate the energy that I'm going to need to use to break all of those bonds, I'm simply going to add those up. So if I use the calculator and I just say 436 times 2 plus 497 equals 1369. 1369 kilojoules per mole. Okay, per mole. So that's the energy that it would take to break the bond. Now, you could do exactly the same calculation, and it's in your notes. If you're looking at the X sheets, you'll see to make the bonds. The trick here is that you'll have to look at the number of moles and calculate the number of bonds. So we've got H2O. Let's just do that part first. In fact, I'll go to do it on the next page because that's the determine what it is to make the bonds. I'm not going to complete the calculation. 2 H2O is what I'm dealing with. OH, O. OH. So how many OH bonds have I got? For each molecule, I've got OH and another OH for one molecule. So I hope you can see that's in one molecule. And I've got two molecules, so I'm going to have times 4. So if I go to the table, what I'm going to do is I'm going to find the OH substance, and I'm going to say, there we go, 464 times 4. So you know what, we might as well do it. 464 times 4. Calculator, not difficult to see. What we've got is 464 times 4. So that gives me an answer of 1856. 1856. So here's the interesting thing. When you put in some energy, you then have to give the energy. The atoms join together, they rearrange themselves, they take some of that energy, and in this case, I hope you can see they've taken more energy than what we used to break the bonds. So what we've got is 1369, and what we used to make the bonds is 1857. Now the difference between that is actually the energy that's going to be given out after the formation of the particular bonds. So that calculation is done for you in your X sheets. I hope you follow it and make sure that you've got that sorted out. Now, you know what? There's one last thing that I just want to deal with, and that's the definition of oxidation number. So just give me a second and we'll go straight to that. Here we go. We've got oxidation numbers. What are we talking about? Oxidation numbers are very important in chemical bonding. What we need to recognize, it tells us if the oxidation number is negative. A negative oxidation number, negative number, tells us that it is electron rich. The word we're looking here is electron rich. It can donate electrons. If it is a positive number, use a different color, positive number, then it is electron poor. Now, what this means, it tells you when we've got an atom joined to another atom, which one is getting more of the electrons. There are a set of rules that you're going to need to know. The most important rules are the following. I'll just give you 3, and we'll apply these in some of the examples. Any atom, one atom that's on its own has an oxidation number. I'm going to abbreviate and say ox number. Don't do that in the exam. Oxidation number equal to 0. If it is an ion, the oxidation number will be equal to the charge. The next one, if it's a molecule, the total oxidation number will be 0. And the last one, sometimes gets us out of jail, hydrogen in any compound, in a compound, has an oxidation equal to +1, oxidation number equal to +1. And the last one, oxygen in a compound, has an oxidation in most cases of -2. Let's go to those example questions right now. Corrugated iron sheets need to be painted regularly to avoid rusting. The following shows how flakes form. So we've got Fe plus O2 to give you Fe2O3. This is not balanced, it's unbalanced. It now asks the following questions. Give the oxidation number for each of the atoms in the reaction. Okay, so let's go and have a look. Remember the rules of oxidation. If it is an atom on its own, its oxidation number is 0. If it's a molecule, then the total oxidation number is 0. I put the totals down at the bottom. And then if you're going to say the whole molecule is 0, and there are 2 of them, then each atom must be 0. They're exactly the same, so that's why the unit oxidation number for oxygen is 0. So if I were to write this answer down, I would say Fe, oxidation number 0, O2, oxidation number 0. Now we come to this one. So we've got Fe2O3. This is iron 3 oxide. Now, the way we're going to determine the oxidation number is we're going to apply the rule that says, let's put in the oxidation number of oxygen, which is -2. So -2 times 3 gives us -6. Now, the whole thing has to add up to 0. So what plus -6 will give you 0? Well, that's not too difficult. +6. +6 divided by 2 means that iron is +3. So answer iron +3. Remember to put the pluses and negatives in if that is the case. See as well, notice as well that the oxidation number of an atom is very similar to its valency, and that's one of the ways we can check. Now, here's an interesting question because it relates to the idea of oxidation and reduction. And I just want to, when we're talking about oxidation numbers, just remind you about something that you might not know or you might have forgotten. When we talk about oxidation, the word oxidation means that there is a loss of electrons. And I remember that by saying OIL. Oxidation is a loss, and reduction is a gain of electrons. So I remember that by saying reduction is a gain. So the mnemonic memory tool I use, OIL, oil, RIG, RIG, oxidation is loss, reduction is a gain, is a very helpful tool to answer these type of questions. So it says to me, which substance is reduced? In other words, which one is undergoing reduction? We want to know where is reduction happening. So reduction, remember, that is a gain of electrons. Gain of electrons. So if we look at the oxidation numbers from our balanced equation, we want to see what's happening in each case. Well, it doesn't take too much to recognize that iron has gone from 0 to +3. Now, if you're going from 0 to +3, what's happening? Let me show you. If we put it on a number line, 0 over there, and we've got +3, then what's happened is we might think we're gaining positives, but another way of doing that is we're actually losing, this is a loss of 3 electrons. Because over here it was neutral, same number of protons as the electrons. So what we want to do is to recognize what happens when we go the other way. In other words, when we get more negative, that's what we're gaining electrons there. We need to make sure that we've got that all sorted out. So let's go back to the equation and let's see what else is happening. Oxygen starts at 0 and ends up at -2. So I hope you can see that is an increase in the negative. If it's an increase in negative, that's a gain. So it started at 0 and it ended up as -2. This is a gain of electrons. So what we had to recognize, which substance is gaining electrons, which is being reduced? Well, in this case, I don't think it's too difficult to recognize that oxygen is the answer. So oxygen is being reduced. It is undergoing reduction. It is gaining electrons. So now the next term. We read the question, it says, name the reducing agent. This seems to be quite complicated because we've got reduction, we've got reducing agent, but I've got a way of remembering it. So I want to show that to you. After learning those mnemonics, here's another mnemonic that I want you to remember. Now, when we say reducing agent, I'm going to write that as Ra. Now, this reducing agent is a chemical agent. Think of it as 00 chemistry, not 007, but he's a mysterious thing that walks around inside the reaction, making something happen. He's there to make the stuff actually react. And it does it by doing something very special. The reducing agent is a really cool agent because he donates, or she donates. Reducing agents donate. And so that's why I said they're cool, because another word for cool is rad. So there you go. Reducing agent donates. So if you remember that a reducing agent always donates electrons, then we've got to ask ourselves, where were the electrons coming from? Who donated the electrons? Now look here. Oxygen gained electrons, but the iron lost electrons. So the iron is the reducing agent. It is the thing that is donating electrons. It went from 0 to +3. It underwent oxidation. This is oxidation, where this one is reduction. The green was reduction, the pink was oxidation. The reducing agent is the iron. So there we are. That's the reducing agent. It makes reduction happen, whereas oxygen takes electrons and it is the oxidizing agent. So the oxidizing agent, it makes oxidation happen. We would say, the way to remember it, oxidizing agent takes electrons. We know this is electrons in both cases, so I remember it by making the word OAT. So reducing agent donates, oxidizing agent takes, and we've got it all sorted out. The reducing agent, if I fill that in then, the reducing agent identified from the one that it was going from 0 to +3. It's the source of electrons, it is the iron. So let me write that in the space here. The reducing agent is iron. Notice it says the name. So I mustn't give the formula, I must give the name. Now, the next question is quite important, and we've done some like it. It asks for the Lewis structure of oxygen. Now, please notice something here. Oxygen here, we need to understand that when we talk about oxygen, we're not talking about oxygen atom. We're talking about oxygen, the substance. Oxygen, the substance, is a diatomic molecule. So it's O2. And even in the equation, we've got O2. So remember that. So let's draw the Lewis diagram underneath here. Head it Lewis diagram. Of O2. Now, we did one similar, or we did the same one, just for the oxygen atom earlier. Remember, oxygen's in group 6, so there's 6 electrons, and 2 are lone pairs, and 2 have the ability to bond. They're unpaired. So these are the lone pairs over there, and we've got the other oxygen atom, over here. I'm going to draw them as crosses. And if I circle those, and I now pick them up and pull them together, hopefully we can get them close enough to match. I just want to pull that one, not that one. Just pull that one up there a bit so it's, you can see very clearly the bonding pair, and there's the second bonding pair. They will relocate, so they form two bonds. This will be a double covalent bond. Double covalent, because it's sharing, bond. And notice, because it's oxygen with oxygen, it will be a non-polar bond because there's equal sharing. The reason is equal sharing. Overall, oxygen is non-polar as well. So even though the bonds, there's equal sharing, the molecule is also, it's a linear molecule, equal sharing around that. So I hope you've got that. There's the Lewis diagram, and we've illustrated the bond pairs. Notice that we've got these pairs over here, and that's quite important to notice. These ones, they are known as lone pairs. They aren't shared. They are lone. They're on their own. This is a lone pair of electrons. Question number 2. Let's go to C. What is the difference between the type of bonding in chlorine and in magnesium chloride? Well, that's quite easy. We've got metal and non-metal in magnesium chloride. You got the clue? What's that? Metal, non-metal, work it out. Where in chlorine, we've got sharing of electrons. It's diatomic. So let's make sure that we've got it. Chlorine, it's covalent bonding. Covalent. Where in magnesium chloride, I hope you can see that this is an example of ionic bonding. The atoms of magnesium lose 2 electrons each, chlorine gains them, and so we go on. Okay, here's another question on oxidation number, and this time we're asked for the oxidation number of chlorine in each of these cases. This is an interesting question because it shows that chlorine, even though it's a non-metal, can have various oxidation states. That tells us whether it's electron-rich or electron-poor in each of the states. The way we're going to do it, we're going to assign oxygen as a -2, and then use the rules -2, -2. There's only one of them. So this whole thing must be +2 divided by 2. So the chlorine in this case has a oxidation state of chlorine +1. Okay, hope you can see that. Total was +2, divide by 2 gives you +1. What about this one? We've got -2. Let me change the color, sorry. -2 times 2 is -4. That means that one is +4. There's only one of them, so the individual oxidation number for chlorine is +4. The answer, chlorine +4. Now what about the next one? Cl2O6. I hope you can see these numbers are getting bigger and they're changing in their way. I just want to erase that so we've got some space to put it between the lines and fill it in. We'll start with -2 times 2 is -4. That means that this, sorry, I've done that one. Erased it and just redid it. So we're going to start with the -6. -2 times 6 is -12 plus 12 divided by 2 is going to give me an answer of +6. Okay, so in this case, number 3, chlorine has an oxidation number of +6. My last one for this question, we've got Cl2O7. So if we do the numbers like we did them before, hope you can do it. -2 times 7 is -14. Now remember, the whole molecule has to add up to 0. It's neutral. So this one is +14. Plus 14 divided by 2, plus 7. There's the number that we're looking for. So if we change the pen color again, we'd say for this one, chlorine is plus 7. Now look at that. Chlorine in each of these cases has a different oxidation state. Over here it's plus 1, there it's plus 7. It's lost 7 electrons. It's kind of like having lost 7 electrons. It's electron poor. It has given away all of its electrons. It was a good reducing agent. If it was there, it's lost only 1 electron. It would like to have gained electrons, would have made it an oxidizing agent. Okay, so just bear that in mind. These are different oxidation states for chlorine, and it is a useful exercise. Right, question number 3. Here is our question about the shapes of molecules, and it's an important one. So let's go and have a look at it. Well, what's this molecular shape? We've got a small one and a big one. Well, I think we can do this easiest if we identify the substance. The formula of a substance with this shape, well, if we take the small ones as being hydrogen, then that could be hydrogen with a non-metal, with a non-metal, something like chlorine. So HCl. What's the shape? Well, it's clear. It's in a straight line. It's linear. Let's work down in the table that you've got. What's the polarity of the bond? The difference between hydrogen and chlorine, there is an electronegativity number difference. Chlorine's 3,5, hydrogen's 2,1. If you subtract them, it's quite a big number. So this is a polar covalent bond. The polarity, it's polar. What's the polarity of the molecule overall? Well, there's no symmetry here. The one end of the molecule is going to attract electrons, the chlorine end, delta negative. This end, delta positive. So the whole molecule doesn't cancel out, doesn't spread the electrons evenly, so the molecule is polar. Right, we're going to the next one. This one is, can you see, like that? If that was a hydrogen, that's a hydrogen. The example that I would use this is H2O, water, or H2S. I think you can see that it's bent, also called angular. And if we look at H2O, the polarity of the bond, it's definitely polar. And as we explained earlier, the molecule is also polar because it's got 2 lone pairs, making the top part of the molecule negative. There we go. Has 2 lone pairs. As soon as you've got extra electrons in the form of lone pairs, bent substance like that, this end will be positive, that end will be negative, and that's why the intermolecular forces, not a topic for this lesson, but something that you will have learned about, intermolecular forces between water molecules are so strong. Polar molecules, strong intermolecular forces. Okay, what about this one? Well, that's pyramidal. There are 3 of them. It looks like there's a lone pair over there. Pyramid, like a pyramid, pyramidal. The example I gave you earlier was ammonia. And we've just done one to show that the difference between hydrogen and nitrogen is significant. It's polar. And we know that it can gain and form a dative covalent bond. So the lone pair is going to make sure that there's a negative end to at the top. This top structure here is going to be delta negative, whereas this bottom end is going to be delta positive. So overall, the molecule is polar as well. Okay, sure, we've got 2 more to do. So let's do them. Next page. So here we've got the next structure. Well, the black represents carbon. So let's talk about this as CH4, which is methane. And the shape of the molecule is tetrahedral. If we move down, the polarity of the bond is polar. But now remember what we said. Because of the symmetry of the molecule itself is non-polar. Okay? And finally here we've got the example of carbon dioxide, something that we've just dealt with. It is linear. But now the interesting thing about carbon dioxide is because of its symmetry, although the bond is polar, it's not sharing equally, what we need to recognize is because of the symmetry, what we've got is this sort of structure. We had it just now. I'll just quickly build it again. And we put the second bond in, double bond over here. So you can see this bond between the carbon and the hydrogen, CO2, O over here, C over here, O over here, it's nice and linear. So even though the carbon pulls some of the electrons to this side, and we might get a negative forming, the oxygen might pull, is more electronegative, so it pulls, so we get negative over there, negative over there. There's an even distribution of electrons because the second bond actually has delocalized electrons. So overall, there's an even distribution, and so carbon dioxide is also non-polar because of the symmetry of the molecule. And the way we know that is that dry ice actually sublimes. So when it's in its solid state, bonds aren't very tight, and gives us some idea why carbon dioxide is actually a non-polar substance. The molecule is. Study the values given in the table below and answer the questions that follow. So here we've got different bonds and bond energy measured in kilojoules per mole of bonds, giving you a nice comparison. It says, question 4.1, identify the most unstable bond. Now, an unstable bond is one that doesn't really exist in normal everyday life because it's so unstable. It will fall apart. And it will also have a very low bond energy. So let's go and have a look at that. Well, immediately you should recognize that this doesn't happen very often. Nitrogen to nitrogen is normally a triple bond as a molecule. Nitrogen to nitrogen, look how weak it is. Has a low bond energy, and it's the lowest of all those on the table. So I would say that nitrogen to nitrogen, single bond, is the one that we must identify. So that's the one that is the unstable. And the reason it is that it is unstable because it has the lowest bond energy. Now, next question, what is the general relationship? Now, there are exceptions to trends between the size of the atoms and the bond energy. So what I'm going to do is I'm going to select a couple of molecules, and to make it fair, I'm going to choose those that are all of similar type. In this case, let's choose the diatomics. So I'm going to say, let's start with hydrogen, H2, then O2, and let's say N2. And let's look at the bonding that's happening there. That will be a single bond. This one will be a double bond. And this one's a triple bond between those. But in each of these cases, the size of the atom is increasing. So what we can do is if we look at it, and we have a look here, and we see hydrogen is 436. Write that down for hydrogen, 436. Then what about oxygen? That's 497. 497. And the triple bonded nitrogen is 945. Now, 945. So what you're seeing is a general trend that as the size of the atoms increase, hydrogen increasing is bigger than, hydrogen is the smallest, then oxygen, then nitrogen, then the bond energy is increasing. But some of you might say, but hold on, you're getting more bonds as well, and that's true. So we've established by looking at those that for the number of bonds as well as for the size, there's an increasing effect. As you increase the number of bonds, you're getting more, but the size is also increasing. So we've got an idea here. But let's confirm our trend. If we say that if this is our hypothesis or our statement, that as the size increases, bond energy increases. Size of atoms increase, then bond energy increases. So we've got to make that conclusion just from here. And some of you might be saying, well, we better just compare and do a fair test. If we're doing hydrogen to hydrogen, let's take another substance that is a single bond. Well, what about carbon to carbon? We know that carbon is 12 times bigger than hydrogen, so let's go and check out what those values are. We know that hydrogen was 436, 436. Well, what is carbon? 12 times bigger. Carbon number 12 on the periodic table, 347. 347, what's happened? 347, the number has decreased. So as the size of the atoms increase, the bond energy increases. No, it doesn't. We've got it wrong. Our hypothesis was wrong. We've shown, if we look here, that as the size increases, that was 1, size increases, the bond energy increases. But here we've shown that it's not true. As the size increases, the bonds decrease. So it depends on, that's decreasing. So what I want to suggest to you is from the data that has been given, you could make different conclusions as long as you substantiated it. In fact, the first example shows multiple bonds. Real thing is that if we compare in a fair way the fact that you've got an increasing size, then what's going to happen is the smaller that the atoms are, the closer they are, the more difficult they are to pull apart, and that's kind of like an intuitive thing. So smaller atoms are actually bonded together stronger. Smaller, we've denied our hypothesis, smaller atoms, stronger bonds. And you can check this out if you want to by comparing some more data. Let's just quickly do that. We haven't got enough to look at in terms of combinations on this sheet, but there are some other tables that you could look at. Take carbon and compare it to a whole lot of other things. So say carbon and oxygen and carbon and iodine and carbon and fluorine, and get a comparison. And I think there's a question that's coming up on that. Okay, so on the next question, 4.3, which bond is the strongest? Well, we've picked it already. The one with the biggest value, there you go. It's a triple bond. The reason that it's the strongest bond is just that. Nitrogen, triple bond, it's the strongest. Why? Because it has 3 bonds. Not all of the bonds are equal strength. The first bond is stronger than the other 2, but so it's not a multiple of 3, but it is stronger because you've got 3 bonds. Explain the difference in bond energy between this triple bond and that single bond. Well, it's simply that factor that I've just mentioned. That one is 945. This one is 148. It's only a single bond. You add 2 more bonds, you actually pull the atoms closer together. It's not just multiplying by 3. So the difference is here, this one is larger, stronger, this one is weak. And the reason is this is single and this one is triple. And the triple bond is so much stronger because the atoms are drawn closer together. Right, let's just make sure that we've got that. I just want to compare the next one. And here we've got the comparison between a double bond carbon and a single bonded carbon. And again, what are you going to say? That the double bonded carbon is, you're going to expect to have a higher energy than the single bonded carbon. But notice they're not double the amount. In this case, it's slightly less. The effect of that second bond isn't as strong as the triple bond, but the double bond is definitely stronger because it's pulled the atom slightly closer together. Okay? Last question, question number 5. We're looking at relating the strength of the atom to the size of the atoms combining again. And the first thing that we're going to say, chemical bonding results in the substance's increased stability of a substance. And we have to say true or false. Well, there is a diagram that we sometimes use about the potential energy of atoms, and as they come closer together, they become more stable. And so this statement is true. The ones that have a better energy state because they are storing energy. So the length between the atoms is the smallest. They're small length, and that gives them the stability. the bond length is the smallest. When they're far apart, they're not very stable, they can fall apart. When they're close together, too close together, they have too much energy, but in their ideal state, they'll be the most stable. So the statement is true. Question 5.2, the chemical bond with the greatest bond energy. Now, what we've got to do is look at this. CF, CO, CN, and CC. And the only way we can do this is to compare the size of the atoms. So if we say carbon is the common one on this side, and which ones are bigger or smaller? Well, nitrogen is going to be slightly smaller than carbon, and oxygen is going to be slightly smaller still, and fluorine is the smallest. So this one is the smallest atom, it's the smallest, and so because it's the smallest, in this bond, it's also the most electronegative, which is another factor. It has the highest electronegativity, neg. Although that wasn't what we were asking about, but we could use it as a factor. It's the smallest atom and it has the highest electron, and therefore, for those two reasons, it will be the strongest bond. Okay. So you just had to give one of those two reasons. For the reaction, 2 moles or molecules of ozone gas forms 3 molecules or moles of oxygen gas. It says, do the number of moles of molecules increase, decrease, or remain the same as the reaction proceeds? Now, this 2 in front here and this 3 in front there is the balancing coefficient. It represents either the number of molecules or the number of moles. Moles is just a special word for counting molecules. When we do chemical reactions, we're doing them on a big scale. Millions and millions and trillions of atoms or molecules combining. And so moles is some term that we will use to do that. And all we're asking, is it increasing or decreasing? Well, we started with 2 molecules here, and we've got 3 molecules. So I guess the word is increase that we're wanting to see here, because we're going from 2 to 3. And it's a very important idea that you understand what these balancing coefficients mean. It is a ratio of the things reacting. So just a question to stretch you into doing some thinking. So here we go with another question, and it's almost the very last question that we're going to be able to do today. So let's make sure that we've got it. It says, study the reactions below. We've got iron in a solid forming iron 2 plus as a solution, plus 2 electrons, and hydrogen ions plus oxygen plus 4 electrons to form water. And it says, indicate the oxidation numbers of each substance, and then identify the substances that are reduced and oxidized. And so it gives us some clues about that. We're going to do it straight over there. So let's do the oxidation numbers, and let's see what's happening here. We say that oxygen is 0. This one has a charge of +2, so it has an oxidation number of +2. This one is +1, it's the iron. Oxygen is 0, and in hydrogen is, in water at least, hydrogen is 1, and oxygen is -2. Let's check if that works. -2, and that should be +2. Divide by 2, and it's right. So let's see what's happened. What's happened to the iron? So we've assigned the oxidation numbers, and I hope you can see that iron goes from 0 to +2. It also tells us that it has produced some electrons. That means it's lost electrons. So what's happening to iron? Iron is losing electrons. It is undergoing oxidation. So iron is oxidized. So we're going to say iron undergoes oxidation. And then the next thing is, well, what's happening in the next case? Let's have a look and see. Here we've got oxygen at 0. We've got hydrogen at +1. Where has there been a change? Well, I hope you see that hydrogen was +1. It's still +1 over here. Nothing has happened to it. We can kind of think of this as a spectator. It's sitting on the sideline just watching what's happened. But look what's happened to oxygen. Oxygen went from 0, and it's got all the way to -2. So what's happened to it? That is a gain of, for each oxygen atom, please notice, it's saying plus 4 electrons, but each oxygen atom individually gains 2 electrons, and there were 2 electrons, 2 atoms present, so that's how we get 4 electrons. So oxygen is the thing, the oxygen atom, oxygen as part of O2 has undergone reduction. It is reduced. So with that, make sure that you study hard, and we will see you again quite soon.